Hi, we are going to talk about circular motion. Before we dive in, I want to point out that circular motion works like linear motion. We just have different names for the variables and different units. So first we have angular position. This is the position of a particle traveling in a circle with a fixed radius, and it's measured clockwise from the positive x-axis. Angular position is given by the angle theta, and its units, are radians, which are fake units. And this is part of this we can see in where radians comes from. It is the arc length, so this distance, divided by the radius, this distance. Those are both distances, and if they're in the same units, the units cancel out. Um, So anyway, angular position is really just the angle when it's rotating around in a circle. And we list that in radians. In radians, one revolution, which is one time all the way around the circle, is 360 degrees, and it's also 2 pi radians. So you can use this relationship between 360 degrees and 2 pi radians to find that 1 radian is 57.3 degrees. And I don't remember if I say this later on, so I might repeat myself, but you might, in some of the problems with circular motion, you might see something that's in revolutions per minute or RPM. We're going to do an example with that. But to figure out what that is in radians, you just use this relationship where 1 revolution is 2 pi radians. So we have these diagrams, these motion diagrams, particle motion diagrams from linear motion and circular motion. So remember, the points are the same time apart, but they show the distance apart. And so here on this example, same thing, where we start at 0 seconds and then 5 seconds is a quarter of the way through a revolution. So that's a slower moving angular speed. And then in this one, in the same 5 seconds, they travel halfway around the circle or half a revolution. So that's larger. And we see that the angular displacement, which just like linear displacement, is the difference between two angular positions. So this angular displacement is bigger than this one, just like how this linear displacement is bigger than that one. So then we have angular velocity, which is the angular displacement divided by the time interval. And that is, again, just like the linear velocity, which is the linear displacement divided by the time interval. And so we can see that in this example, the angular velocity was larger. And in this example, the angular velocity is smaller. So one thing to know that is unique to circular motion is how we define positive and negative. So for linear motion, we define positive to the right, negative to the left, and positive up and negative down. When it comes to angular motion, we define counterclockwise as positive and clockwise as negative. So angular displacement, we've already talked about it, but again, just to lay it out clearly, it is the same thing as the linear displacement. It's just the final angle minus the initial angle is the angular displacement, and that's also equal to the angular velocity times the time interval. And sorry, I didn't say this already, but the angular velocity is this curly w, which is omega, lowercase omega. I almost forgot what it was for a second. Okay, next up, let's talk about period and frequency. And really, first, let's talk about one full trip around the circle. So if we go all the way around the circle one time, our angular displacement is 2 pi radians. Because remember, one trip all the way around the circle is 2 pi radians. And then our time interval for this is what we define as period, is this capital T, and a period is just the time it takes to make one full revolution. So we can use this information to connect the period to the angular velocity, because our angular displacement is 2 pi radians and the time is the period. And so we end up with this equation relating the angular velocity to the period of the rotation. And also, just to add in, there's frequency, which is 1 divided by the period. And so you can also connect that to angular velocity. And that would just be 2 pi radians times the frequency. So we can also, so just because something has angular velocity doesn't mean it doesn't also have linear velocity, or we refer to it in this case as tangential, and it's tangential because it's tangent to the motion of the circle. So like anywhere you can make a straight line and it would be tangent to the circle, and that would be the direction of the tangential velocity. So in this case, when it comes to the circumference of a circle, the circumference is 2 pi times the radius. And so we can also connect the linear velocity or tangential velocity to the period by taking the distance of 2 pi times the radius divided by the time, which is the period. Sorry, I was making sure I had it all on there. If we can relate both angular velocity and tangential velocity to the period, well, that means we can relate them to each other. And so what we find is that the velocity is equal to the angular velocity times the radius. And this is when the angular velocity is in units of radians per second. So you can't use, sometimes you'll be given an angular velocity in RPM or revolutions per minute. You can't use that. You have to convert it first before getting the tangential velocity. So just like with linear motion, we have angular acceleration, and that's the change in the angular velocity divided by the time interval. And this is, there's just an added interpretation in understanding both the direction and the sign of angular acceleration, just like how in linear acceleration, you want to know if the object is speeding up or slowing down, and that will tell you, if you know the direction of the linear motion, it will tell you the direction of the linear acceleration. So here, for example, we have the angular velocity is positive when rotating counterclockwise, because counterclockwise is positive rotation, and it's negative when it's rotating counterclockwise. And so the same relation works with angular acceleration. It's just like in general when it's pointing in that direction. But the thing to remember that makes it sometimes challenging, but we've done this with linear acceleration, is that you need to know what the direction of the angular velocity is, and then if we're slowing down, speeding up, or staying the same. So it looks like in this case, the angular velocity is positive, and then we can, I know it says here, but we can even look at our particle diagram and see, okay, the spaces are getting further apart, so it's speeding up. So that means both angular velocity and angular acceleration are in the counterclockwise direction, making them both positive. And then in this example, instead, it's rotating counterclockwise. Clockwise. Yeah, counterclockwise is this one. Clockwise. And we can see that the points get closer together, so that would mean that we're slowing down. So angular acceleration is going to point in the opposite direction, which is counterclockwise, which is positive. And then again, with this one, so here looks like we're rotating counterclockwise, so angular velocity is positive, but it's slowing down. So angular acceleration is in the opposite direction, making it negative. And then in this one, we're speeding up and we are moving clockwise. So the angular velocity is negative and so is the angular acceleration. So I know this looks weird, but it really is the same kind of logic as the linear motion. You just have to remember counterclockwise is positive and clockwise is negative. And here is a useful table showing how the linear and circular variables and equations are very similar to each other. So we have the position, velocities, and acceleration, and then we even have equations that we can use in a similar way. We even have a version of the long kinematics equation that we can also use in angular motion or circular motion. Another thing to note, so again, we're thinking about these ones are the tangential velocity or linear velocity of circular motion, like of an object in circular motion. So, and the acceleration is the change in velocity divided by the time. And so we can figure out the direction of the acceleration by using the velocity vectors. So if we have here the initial velocity vector and the final velocity vector, change in means final minus initial. So we draw the final first, then we draw the initial at the tip of the final. And then we get a change in velocity by drawing from the tail of the final to the tip of the initial. Oh, and sorry, this is, so it's subtracted, so it's we're adding the negative. And so what that gives us, that change in velocity gives us the direction of the acceleration. And the point of that is to show that in circular motion, as long as it, is circular, the direction of the velocity is changing all the time, which means there has to be acceleration because acceleration, change in motion requires acceleration. And if we pick just, it looks like they picked these points, but we could pick any points on the circle to do vector addition, subtraction, really. We find that no matter what 2 points you pick, the acceleration points toward the center of the circle. And using this, not that exact thing, but using linear variables in circular motion, I'm not gonna, don't worry about being able to derive this. You're not gonna have to. I just want to show you where this comes from. We can get a relationship between the acceleration and the velocity and the radius in circular motion. And this would be that acceleration pointing toward the center of the circle. So it's v squared over r, and it just comes from some relationships that we don't need to worry about. So what this is called is centripetal acceleration. And centripetal here means center seeking. So it's just indicating that it's pointing to the center of the circle. And you can also find that if you have the velocity and the radius, you can use that to find what the centripetal acceleration is. So an object moving in a circle at a constant speed, so like the magnitude of the velocity isn't changing, but the direction is changing, so there is acceleration, and that acceleration is toward the center of the circle. And if there's acceleration, there must be a net force. So the net force, we also can call this centripetal force, but it is also just in general the net force in circular motion. Showing that if an object is experiencing circular motion, there must be a net force pointing toward the center of the circle, because circular motion requires acceleration for the center to change the direction of the velocity and keep our object in circular motion. This is also true for cars going around curves or up or down hills. So you can imagine this kind of going on a curve. Maybe you could think of an exit ramp on the freeway. So the car's driving, here's its velocity. And the center of the curve, which you can't always see, it's not always a complete circle, but it's out here at the distance. And we'll also see examples later this week with, like, if we're on a hill and the car is here, the center of the circle is down below the car. And if the car is in a dip, and it's here, and the center of the circle is up above it. But we'll see more of that later. Okay, and now we're going to do an example. So I'll read it first. A large wind turbine, typical of the size and specifications of a turbine that you see in a modern wind farm, has 3 blades connected to a central hub. The blades are 50 meters long and rotate at 10 revolutions per minute, RPM. What angular speed does this correspond to? What is the speed of the tip of the blade? What is the speed of a point 25 meters from the hub? And a 5-kilogram bird lands on the end of one blade. What centripetal force does it experience? Okay, cool. So, I've already drawn the turbine for you. And let's start with the angular velocity. So angular velocity is given here in revolutions per minute as 10 revolutions per minute. Now, I already said we can't use it in revolutions per minute. Like if we're finding things like velocity, or even actually here in the question, it's treating the 10 RPM as, well, they're treating it as like a frequency. But anyway, they want us to convert it when they ask for angular speed. They're saying, okay, give this to me in radians per second. So let's do that. Okay, so we have 10 revolutions per minute, and we remember that 1 revolution on the bottom, so it cancels, is 2 pi radians. And then to convert 1 minute is 60 seconds. And I will just calculate this really quickly. 10 times 2 pi divided by 6. Okay, that gives us an angular velocity of 1.05 radians per second. So that's our angular velocity, or angular speed, I guess is technically what they're saying in here, because we don't know the direction. And then it asks us for the velocity or speed at the tip of the blade. So the velocity equals the angular velocity times the radius. So the radius here, it's asking for at the end, so that's 50 meters. And then the angular velocity we just found is 1.05 radians per second. So we can plug this in. 50 meters times 1.05 radians per second is about 52 meters per second. So that's the velocity at 50 meters. Okay, and then it asks us for the velocity at a point 25 meters from the center. So now we're looking like halfway. So let's see, our radius is 25 meters. Our angular velocity is the same because angular velocity is constant no matter how far you are from the center. And so is angular acceleration. But linear velocity depends on how close you are to the center. And we'll get more into that. Not today. Okay. So this is just going to be half of what we found before because we have half the distance. And this is showing us how radians aren't real units because we end up with meters per second, even though we are not canceling out radians because again, they're technically not real units. It's kind of weird. Okay, and then for the last thing, it asks us for let's see, a bird lands at the end of one of the blades, and we want to know what force it's experiencing. So the force is the mass times centripetal acceleration. I'm going to give it that C subscript so we know that's what it is. And that is v squared, the velocity squared, divided by the radius. So we don't even have to calculate the centripetal acceleration. We can just go straight to finding the centripetal force or the net force. So we have 5 kilograms. Let's see, we're on the tip. So 52 meters per second squared divided by 50 meters as the distance. So let's see, 5 times 52 squared divided by 50 gives us a net force of 270 newtons toward the center. There you go. That is our first example of angular motion. And you can see how we went kind of back and forth between angular motion and linear motion and tied force into it too. So that's all for today.